of a cantilever. Okay, and under this load it is going to be formed like this, and we have plotted. Okay, and we have represented this by equivalent bilinear. Here you can obtain this qy, delta y, delta u, and the corresponding value of q. Okay, provided the section of this cantilever is given. Okay, if it is subjected to a vertical load, because in case of a column, a vertical load will also be applied, this P. So in presence of this P also, you can plot it. Are you clear up to this point? Any doubt up to this point? That's what we have covered so far.
सर
Yes.
आपने जो एग्जांपल दिया था इसमें कैंटिलीवर पे यहाँ पे लगा के लोड लगा देते हैं, यहाँ पे थीटा पी बनता था प्लास्टिक रोटेशन वाला.
Okay.
और here is one another example. And this beam is rigid up to this, and this it would also rotate like same like this. Then what is the difference between these two cases?
In one case, this is flexible and this is rigid.
Yes.
Another case, this is pin.
Ah.
So you are saying that this and this are same. What is the difference?
What is the difference?
Okay. So the question which Vijay has asked is that we discussed this, that we had a hinge here and we have applied this.
Yes.
Okay. And in another case, this portion of the beam is rigid
Yes.
and it is rigidly connected and we have applied this.
Ah.
Okay. So what is the difference in the two? Especially at this junction. Perhaps your interest is here. But is there any difference here?
Ah.
So can anybody tell me what is the difference here in the two cases? What is the difference here and here? Here pin is there, here it is rigidly connected. So what will be the difference? Difference will be in moment transfer. So here the moment transfer cannot take place, but if it is plastic hinge, if it is not a pin, physical pin, but a plastic hinge, then moment transfer can take place. Up to my, the moment transfer can take place. So that is not the difference. Where is the difference? The difference is in rotational compatibility. Okay? So here the rotational compatibility of left and right side will not be satisfied. The angle on the left side and right side may be different. Okay, but here it is not possible. This is rigidly connected. Rigid joint means what? That the compatibility of the rotation is to be satisfied. So in the first case, up to this point, it will remain straight,
Yes.
horizontal. Beyond this point, it can move, and this angle theta which you have is at this point.
Yes.
So you can see at this point the left hand side and right hand side elements are having different angle. That means the compatibility of rotation is not satisfied in this case. Whereas here what will happen, if it is deforming like this, and whatever angle you have here, this tangent, this rigid portion has to have the same angle. So this angle has to be satisfied. So here there is no relative rotation. The rotation is same. Here the rotation is concentrated. Okay. So compatibility of rotation is not satisfied in case of hinge, whereas in case of rigid connection the compatibility is satisfied. It is something similar to this case. It will be better understood if you consider this case. A frame, let me make the beam rigid for simplicity, and then in the next case, same frame, but I have provided hinge here, release or hinge here. Okay, can you plot the deformed shape in the two cases?
Yes.
Please do that. What difference it will make? Which case is this? So the beam is rigid, so beam cannot bend. Beam will remain straight in this case. Rigid beam means what? It cannot bend. There will be no rotation of the beam. Okay. Yes, sir. So will there not be any deformation? So rigid means that the two ends will remain. The distance between the two ends will remain same. That doesn't mean that it cannot move. It can move as a rigid body. So a rigid body movement will be there. So this rigid beam cannot be formed. There will not be any deformation here in the beam. So there won't be any deformation in the beam. Right, beam is bent. Beam is not bent. No vertical load. There is horizontal load also. And even if vertical load is there, it is rigid. So any rigid element cannot bend even under vertical load. With pin or without pin? Without pin. So without pin, I told you that the compatibility should be satisfied. So what is the compatibility? The beam and the column are perpendicular to each other. So those will remain perpendicular. But here the angle has changed. Yeah, the first case is regular, second case is the same problem. Beam is not going to bend. You have and beam also like this, no? But beam cannot bend. Beam will remain straight. So in the first case, the beam is rigid, so this beam will simply translate as a rigid body. It is not going to deform. And for compatibility, the column here has to be perpendicular to it. So the tangent to the column at this end has to be like this. Here it is fixed, so here also the tangent will be like this. So the column has to be formed like this, like a fixed column, and here will be point of contraflexion. In the second case, again beam is rigid, so it can translate only as a rigid body, and here there is no need for compatibility to be satisfied, but here it will be vertical. So what will be the deformed shape? The deformed shape will be same as that of a cantilever. So it will deform like a cantilever. Okay. Where will be the point of counterflexion?
No point.
This itself will act like a point of counterflexion. So the effective height here is h by 2, and here the effective height is h. Okay. Now imagine this is not a release, it is a plastic hinge. Then what will happen? Then how will be the difference? Same structure, but it is no more a release, but it is a plastic hinge. I have a plastic hinge. Then what is going to happen? What is a plastic hinge? How the plastic hinge is going to behave? Like this or like this? Before yielding, the plastic hinge will behave like this. Okay? So before yielding, there will not be any rotation at the plastic hinge. Okay? But the column will deform as it is deforming here. So before yield, it will behave like this, and after yield, it will behave like this. So can you plot the deformation? How will be the deform shape in case of plastic hinge? Plastic hinge is different from the release. What is the difference? That release cannot take any moment. Plastic hinge can resist moment up to my, but beyond my, it won't take any additional moment. So till my, till yield occurs, it will deform like this, and after that, it will deform like this. You can also extend this case to the same situation where in place of this release, I have a plastic hinge here. Plastic hinge is like a rusted hinge. Okay, so initially it will act as if it is monolithic. Okay, there will be no rotation, concentrated rotation occurring here. So what will happen? It is going to deform like a cantilever. Okay. Then here plastic rotation will occur, and when plastic rotation occurs, what is going to happen? The deformed portion itself will rotate as rigid body. So it is going to. So initially, let's say this was the chord rotation in elastic condition. Now this is the chord rotation. So this theta, this is the plastic rotation, and this theta, this is elastic. So initial theta, theta E, the elastic theta, that is occurring because of the deformation of the beam. Theta P is occurring due to rotation at the plastic edge. So there is no additional deformation occurring. The curvature in this beam is not changing. Whatever curved shape it has acquired at the time of yielding, same curved shape will remain. It will rotate as a rigid body. Okay? So as a whole, it is going to rotate. So now can you plot the deformed shape in this condition when it is subjected to lateral load? What will happen? Yes. Visualize. Like the first one. So that means there is no role of these plastic hinges. That's what you mean?
After they reach.
तो जो भी रह जाएगा वही प्लॉट करो. This is for the shades, for the second, no? There is pin at the top. And this is the third case. But in the third case, initially it will be like one, and then it will rotate, or it will deform like two. So, till ambi is reached, till then, it is deforming as case 1. Let me call this as case 1, this as case 2, and this as case 3. So, in case 3, till yielding occurs, till the moment here reaches ambi, it will deform like case 1. No difference. Okay? And what is the theta y here? The chord rotation. We will join these points. What is chord? Chord is this. Joining the two ends. Okay? And this angle which it is making from vertical, that is theta. The chord, which angle it is making from the original position of the chord. Original position of the chord was vertical. Now the chord has rotated. Tangent has not rotated. Tangent to the column at top and bottom is still vertical. So, yes. This blue, I will use and blue. So, the tangent is still vertical. The compatibility is satisfied. Okay, but the chord rotation has occurred, and that chord rotation is equal to theta y. Now, what will happen beyond this? After that, at the top, it will yield. Okay, and now once it yields, the compatibility in rotation will not be satisfied. Compatibility in translation will be satisfied, but the compatibility in rotation will not be satisfied. So this deformed shape, when it moves further, so what will happen here? The initial curvature which was there in the beam, in the column, that will remain there. Okay. But additional curvature will not occur, whereas here additional curvature will also occur. So you can see here the tangent is no more vertical. Okay. Here the tangent was vertical. Here also the tangent is vertical. But here tangent is no more vertical. This angle is no more 90 degree. This angle has changed because rotation has happened. At the base, still the angle will be 90 degree. Okay. And then the column will deform like this. Our friend was telling that point of counterfracture will shift downward. Will it shift downward? Will it remain same? What will happen? Point of counterfracture will shift upward. Okay, why upward? Because in this case it is at the center, in this case it is at the top. When it will combine, or point of counterfracture in the middle, when the moment at top and bottom is same. What is happening here? The moment at the top is equal to my, but at the bottom it can increase beyond that, because there I have not provided any plastic hinge. It is not yielding. So the moment at the base will be more than m1, and at the top it will be equal to m1. Okay. So point of contrafraction will shift upward, not downward. And then you join this chord. This angle here, this is theta y plus theta. Yes.
Can you repeat why point of contrafraction will shift?
Okay. So in this case, the moment at the top and bottom will be equal. So our point of contrafraction is in the middle. Here, the moment at the base is there, at the top is 0. So point of contrafraction is here. Consider the third case where the moment at the base is more and moment at the top is less. Then what will happen? So it will be something like this, that it will deform less here and it will deform more here. So where will be the point of contrafraction? The point of contrafraction will be, it will shift up. If you draw the bending moment diagram, you can think it like this also. The bending moment diagram will be like this. So if this moment is larger, this moment is smaller, point of contrafraction will be above mid-height. If both moments are equal, then point of contrafraction will be in the middle. Point of contrafraction means where moment is changing its direction. Okay? Yes. Right. The position or the angle of the new chord with respect to the original chord. Original chord was vertical, and now it has achieved this position. So this angle is the total rotation which has occurred. Part of it is elastic up to theta y, and part of it is plastic theta. So this is total rotation. That is theta y plus theta p.
So initial chord is not vertical. Initial tangent was vertical.
No, chord is also vertical in the original position. Original position when my column has not deformed, then the column itself is chord. Chord is just joining its two nodes, two ends. So that is vertical. That is our reference position. But suppose the member was inclined. Let's think this. I have a frame. This type. So here this is the original position. When it will deform, so this tangent has to be parallel to this. Okay, this in any case remains at the same. And when it deforms further, let us say plastic hinge forms and then it deforms. So then you will join this, and you can see that this angle is more than, now sorry, I will not measure it from here, I will measure it from the original position. So the original chord is this. So this angle I have to take as theta y plus. So this chord angle, it is to be measured as the rotation of the chord. Okay. So whatever was original position of the chord, beyond that, whatever change is occurring, that we have to measure. Till this chord rotation will be reflected by deformation of the beam or column. Beyond here, there will be no additional deformation. Okay, but the chord will rotate. So the member will rotate as a rigid body beyond here. Is it clear up to this point? You can visualize up to this point. Now here, earlier we have considered cantilever. Okay, so what will be the my here and theta y here? You can calculate. Can you calculate my and theta y in this case? When it is fixed. Means I have this column and I am giving it a deformation here, delta. And then it is going to deform like this. I have to apply a force here. Let me consider it like this, that will be more realistic. Then it can be. Okay. So it is allowed to translate but not allowed to rotate. Can I plot Q versus delta in this case? You have done already for this case, cantilever. Using that, can you do for this case? You can, because here is the point of counterflexion. So you can consider it into two cases. One cantilever here, another cantilever here. This cantilever is subjected a force Q. So for equilibrium, there is force Q acting like this. So what is happening? This is deforming like this, and this is deforming like this. And at this point, the compatibility is satisfied. You can see that the moment here is 0 in cantilever. Moment here also has to be 0. And if you join them together, you will get this. So if this was delta, how much is this? This is delta by 2 and this is delta by 2. If this was L, okay, this is L by 2. So for this case, okay, this I have already. For this case, again we can plot the bilinear curve. Can you tell me how much will be this Qy and how much will be delta y? In previous case, let's say, how much was Qy? Okay. How much was the Qy here? It was my by L. How much was delta y? Phi by. Okay. Now in case of this fixed, in the same way, can you tell me how much is this Qy and how much is delta y? The moment capacity here, that is my, isn't it? And the section is same as that of the cantilever. Okay, so the yield curvature you can take as phi y. The yield curvature is phi y and section capacity is my. Same section you have used. Only thing is that boundary conditions you have changed. At the top also it is restrained against rotation. In that case, can you plot Qy versus delta y? Can you calculate Qy and delta y? Look at this. How I have obtained Qy as m by L in the previous case? Just considering the length. So moment, capacity divided by length, that gave me qy. Or my is qy into L. Here, what will you get? My by L by 2. So that is 2my by L. How much will be delta y? 2 times delta by 2. Okay, so that is 2 times phi y into L by 2 square divided by 3. So how much is that? Phi by L square by L square by 9. Here it is mu, here it is delta u. How much will be delta u? And how much will be mu? Sorry, not mu, q. Qu you will obtain in terms of mu, as we have done in case of cantilever also. In case of cantilever, how much was mu? Qu divided by L. Sorry, Qu was mu divided by L, or mu was Qu into L. Okay, in this case, how much will be Qu? And how much will be delta u? In the previous case, how much was delta u? Delta y plus delta p. And how much was delta p? Theta p into L. And theta p was how much? Phi p LP into L. Okay. So same way, can you calculate delta u here? That will be equal to delta y plus delta p. Delta y is, just now we have determined, phi by L square by 6. How much will be delta p in this case? Two times of phi p L. Why L? L by 2. So that will be phi p L p L by 2. It is 2 times of L. So this is 2 times. So this 2 will cancel.
Why 2 times?
Because there are 2 cantilevers of L by 2. One cantilever here, one cantilever here. So this cantilever will also deform, that cantilever will also.
And then for the delta y elastic, that also 2 times. Because this is also deforming, this is also deforming.
Yes. So that's why we have taken that also 2 times. Because there are the deformation of the 2 cantilevers will be added. Okay, so now take out assignment number 1 and look at it. Is there anything remaining which we have not covered? If you have to ask anything in assignment number 1, you can ask. Yes. Right.
So asking for this natural crack or this starting of this compound.
Uncracked. Uncracked means what? Uncracked stiffness. When the section is uncracked, no cracking in the section has occurred. So suppose I have a RCC section here. This is the neutral axis, let us say, for the time being. Strain nowhere should exceed cracking strain. And how much is cracking strain? That's here divided by the cracking stress divided by modulus of plasticity of concrete. Okay. So that strain you will determine. And under that strain, whole of this cross section is intact. So how you will calculate stiffness in this condition? Yes, M5. EI is M5 diagram. Okay. So you will plot M5 diagram. Only thing is that this M will go up to M cracking only, and then this corresponding will be phi cracking. What do you think? It will be less than gross, or it will be equal to gross BDQ by 12, or it will be more than BDQ by 12?
More than
Why?
because of the cracking level moment capacity reduced.
No, no, but we are not comparing with the crack. We are comparing with the gross. So this EI effective in this condition, EI effective when strain is less than cracking strain. In that condition, you have to tell me whether it will be equal to or less than or greater than E into BDQ by 12.
Will be equal.
Equal to? Greater than or less than? Only 3 answers are possible. Greater than. Why you say it will be greater than?
Because both quantity will be effective and we will convert equivalent to complete and we will take the whole of this.
Okay. So, but how that will be reflected in M versus 5 diagram? What you are saying is correct, that we have to consider the equivalent area of this steel. So steel we will convert into equivalent concrete. What you have learned in your graduation, we convert this into equivalent area of concrete. So equivalent area of the concrete is going to be more. Okay. Can you prove from M5 diagram that we should consider equivalent area, not the gross area, not BDQ by 12, but we should consider the equivalent area. We should convert this additional we should consider as M times the area of steels. Additional. Why? Why we should consider additional area? The basic principle remains same. EI effective is M over 5. The slope of M5 diagram only is EI. Why that should depend on the equivalent area? Can you prove that? That this EI effective will depend on equivalent area, not on gross area, not on the actual area, but equivalent area multiplied by M times. Why? One thing is you can numerically do it and check yourself that whether you are getting that or not. That is one way. You can always do that. But can you visualize? And then tell that actually what you will get will be coming from the equivalent area. Yes, Vijay.
There, when we are considering that steel and concrete there, and what and beam because we see that there will be strain comparatively between steel and concrete. Therefore, when the strain will be in steel, let's say something, corresponding to that stress will happen.
Right.
Corresponding to stress, I have to provide that much area there.
Right.
But if I provide the concrete area that much there,
Hmm.
that will not, because models of elasticity of the concrete is different.
Okay.
And the models of elasticity of the steel is different. So that I have to compare those area, I have to put additional area that much. Because I know the steel take more force. So I have to put more area for the concrete. And that is the m times of AS. I think.
So, could you get what he is saying? What he said is correct. So, this is the strain diagram. What will be the stress diagram? You plot the stress diagram, then you will get the answer. What will be the stress diagram? Let us say first, let's plot the stress in concrete itself. Concrete has not yet cracked. It is still linear. So, the stress in concrete is linear. So, this is going to be the stress in concrete. Very similar to what we had in case of steel, linear. But here what is going to happen? This stress in steel, this is going to be more. Why more? Because stress is in linear range, stress is E times strain, and E of steel is more. So this is, if the strain in concrete is EC times epsilon, this will be ES times epsilon. So actually the stress will be larger. Okay. And how much larger? ES over EC. So this is the factor by which the stress will increase, because this much portion of the concrete you have replaced by steel. If there was no steel, only this linear curve would have been there. But now you have replaced some portion of it with steel, which is having higher modulus, and due to compatibility, the strain is same in steel and concrete. So at the same strain, steel is going to have more stress because its modulus of elasticity is high. So, and how much more stress? ES over EC. So here also you will get ES over EC. Here also the stress will be high. ES over EC times the stress in concrete. Okay. So actually it is the stress which will increase. If you consider stress to be the same, and you want to consider the increase in the stress in moment, then you can do that by increasing the area also. Okay, but you have to keep in mind the lever arm should remain same. Lever arm is also important in moment. So this area has to increase like this, not like this. You should not increase it like this. Because if you are doing it like this, then the lever arm will also change. So we have to keep the force and the lever arm same. So either you can calculate the larger force by increasing the stress, or the same larger force by increasing the area. So in case of equivalent section, what we are doing? We are increasing the area by m. Okay? Keeping the lever arm same. That's why we increase the width here. We can't increase the width over the whole depth, because in that case lever arm will be different. So actually we are calculating this one. So it was a shortcut of calculating moment, MCR, which you have learned in your graduation. Okay. Finally what we are doing? The same three things which I told you. Equilibrium, compatibility. Okay, and stress strain diagram. Here, when the strain is much lower, less than epsilon CR, it is linear. Okay, so the stress strain diagram remains linear. Strain diagram is linear. Always, in all the cases we have seen, even after yielding, the strain diagram remains linear. Stress diagram changes after. Till yielding, the stress diagram also is linear. Okay, so clear? So you can use the formula by converting it into equivalent area of concrete, but you should be clear. Why equivalent area of concrete? Why not something else? Okay? Any other point? Please go through this. Yes.
Why we are written alpha diagram for M y. So in this, we consider that both of our concrete and steel should not meet.
No. Whichever of them yields first. How do we define first yield? We are calculating not actually yield point. We are calculating first yield point. So what is point of first yield, or what we call first yield? Where the first fiber yields. That first fiber may be of concrete, that first fiber may be of steel. So whichever yields first. Both yield simultaneously. That is a incidence or coincidence. In a very rare case it may happen, but otherwise either steel will yield first or concrete will yield first. Whichever is yielding first, that we have to consider. That will give us my dash, which is the capacity corresponding to first yield. Yes. Okay. I told you that up to yield, there is no difference between confined concrete and unconfined concrete. Both are more or less same. Okay. So the difference does not arise. The difference arises beyond yield. Then the unconfined concrete will fall and confined concrete will have a larger stress strain. Up till yield, there is no difference.
So that falling on the concrete we will consider that the strain based on the falling of the concrete will be considered
at 0.006.
0.006.
Right. But that point you need not determine. If you are determining only equivalent bilinear cover, see, let's see the full moment curvature curve, what is happening. Let's revise that again. Okay. There may or may not be reinforcement on compression case also, and there is confinement as well. So initially, the whole section is intact. EI is greater than EI gross. Slope is much larger, up to cracking. Whole section is intact. Even concrete is resisting forces, stresses in tension. Okay, so effective area is more than BD. Okay, so effective moment of inertia is more than BD cube by 12. Then what will happen? Concrete will crack in the tension. This concrete will crack. So when concrete cracks, spalling has not occurred. It has only cracked. So when the concrete will crack, the effective area will reduce. And when the effective area reduces, this slope is going to change. It will reduce because now EI has reduced. Still, steel is m times, the effective area of steel is m times, but the total area, because a large portion of concrete has cracked. So that's why the effective moment of inertia has reduced, and that's why the slope has changed. Okay. Then what will happen? This steel here, this will yield, or maybe concrete yields at the top. Let's assume that the steel has yielded. When the steel has yielded, what will happen to the slope? of moment curvature diagram. It will reduce further. And beyond this flow from here, this is going to reduce further. Okay. Then what will happen? This cover will stop at 0.0035, and beyond that the reduction will be further. Okay, the slope will further reduce, but it has not started decreasing. Okay, only core will be remaining, and out of that core also, below neutral axis, it is cracked. Okay, and steel has already yielded. So the slope will reduce, it will become almost flat, and it will fail when either steel ruptures or the core concrete, despite confinement, it gets. So even after confining with stirrups, concrete is going to crush at epsilon CCU, which we have written. So when epsilon CCU reaches, then it will become flat. And that will be our endpoint. We are interested in biennial representation of this M5 curve. You can track the full history, what is happening at different places. That's why I don't know whether in the last class it was possible or not. I have told Tajul to teach you the section designer, and there at every strain you can calculate M5 or any given value of M, or anywhere on the curve you select a point. It will give you the strain. Okay, how much strain is there in the confined concrete, and confined concrete, whether confined concrete is intact or unconfined concrete has fallen. So you can trace the full history like that. But for calculation, we will be happy if we just get this. Okay, and from where this curve is passing? First one. Where the first one? But this is M by dash. We are interested in My and Phi. How to get this M? So I have given you two approximations to get this My. One is another is that this My you calculate as M at 0.004. What does M at 0.004 means? 0.004 what? Strain in concrete. Okay. So you consider the whole section of the concrete as unconfined. Okay. Without considering the effect of the confinement, to calculate the moment capacity of that section at 0.004, that will be close to this. Okay, and in the remaining calculation, we can use this bilinear curve. Okay, you may ask why we are drawing this line from the first yield itself. I could have drawn anywhere else. Why at the first yield? Because this EIA factor, which we are calculating and using in our modeling, this is secant stiffness. You can see that stiffness is different. At every point, stiffness is different. Okay, we are calculating secant stiffness corresponding to first yield. So why the secant stiffness corresponding to first yield is so important? I can take secant stiffness anywhere. All these have different secant stiffness. Okay, which one I should consider?
First year.
Yeah, that I have told you. But why that, which I have told you?
Sir, for better first year, the section between elastic.
No. So what? Even if it is elastic. Why secant stiffness there? Why not the tangent stiffness there? This is based on the experience people have gained. Okay. They have calculated the response of a structure during earthquake, and they have found actually during earthquake what will happen? Which stiffness will be there during earthquake? It will be changing. During earthquake, different pulses which cause different levels of deformation. So depending on how much deformation is occurring, the effective stiffness will go on changing. What has been seen that if we consider this stiffness at first yield, it gives a very good estimate of the maximum response. Okay, so that's why this is considered as the representative stiffness. In reality, the stiffness is changing. Behavior is non-linear. The stiffness does not remain same throughout the earthquake. It goes on changing. As the deformation is changing, the stiffness is also changing. Okay. That calculation will be complex. So we simplify that. And simplification is that if we join it from the first yield, people have tried different ways, and then they have come to this consensus that if we take the effective stiffness as the secant stiffness corresponding to first yield, we get good estimates of the final peak response during earthquake. You will see it here. So it is just a protocol, just a standard way of doing it. There is no theoretical proof that this stiffness is the best representative. Okay, it is just based on experience, consensus is there. People have done different analysis, and then they have seen that this gives us the best estimate.
Best estimate corresponding to the peak response.
Peak response will occur during earthquake. Because finally, why we are studying all this? Where will I lead you towards end? Where we are going to reach? Why we are studying all this? Our purpose is to estimate the response of a structure, of a practical structure, not of a cantilever or not of a fixed wing. A practical structure, that too subjected to earthquake. That is our objective. But to reach that objective, we have to understand in simple steps. So that's why we are going step by step. First we have considered a section, then we have considered a cantilever, then we have considered a fixed wing. Later, maybe today, if we move forward, I will tell you how we can go for more realistic structures. Yes.
That is confinement concrete for the very first confinement.
Right.
Means for the first year, only the point is different.
First point is
In both you are saying that would be the same.
okay. So see, first yield is occurring because of the steel. Let us say. Let us assume first point is occurring steel. So when steel is yielding, how much will be the strain in concrete? It will be less than the yield strain of unconfined concrete. Okay? So unconfined concrete yield strain is 0.002. So it will be less than 0.002. And when it is less than, or rather 0.0015, the yield strain we are treating as 0.0015. Below 0.0015 strain, is there any difference in the two curves?
Below 0.005.
0.0015. No. So both the curves are same up to you. The difference starts beyond that.
And sir, question number 4 and question number 5 ASC question number 2013. Means we are taking the FI, E4,
This I have not told you.
Question 5 also.
Okay. See, what I have taught you so far, our column or steel rod was subjected to monotonic load. That's how we have calculated M5. Okay. Now, this column, if I subject to cyclic, and this cyclic load, I go on increasing, or rather the displacement delta. Okay, this delta I go on increasing cyclically. Then what will happen? My curve under monotonic load was like this, which I have represented like this. What will happen here? Can you imagine? Kavan, how to get our PPT folder? PPTs are not there? Okay, we will have PDF then.
ये लास्ट क्लासेस के पीडीएफ है सर.
No, but what about that pen drive which we have copied?
That is in drive.
That is not here.
That is not.
Okay. So, is there last class, last year's, last semester's folder here?
No. What we want?
Okay. I wanted that graph where we have shown cyclic behavior of steel, concrete, and no problem. I can provide. Don't worry. Don't worry. Don't worry. Okay. How to move it? Okay. Okay, so the last question in the quiz I have given you that I have asked you to plot the stress, okay, under this type of strain variation. Okay. Although you could not write, but can you visualize what will happen if I am changing a strain? Let us say like this. What will happen to stress? Or let us take this itself. What is going to happen? Initially, I will plot this in terms of m theta. Okay, I can plot in terms of m phi also, but it is better to plot in terms of m theta. Okay. So, and what is theta? Theta is simply this angle, chord rotation. Okay. And what this theta is giving actually? Theta is giving us delta by L. And M is giving us Q into L. So both are related. M is related with Q, theta is related with delta. Okay. And also with curvature. So we can plot in terms of any axis. So initially, when this delta is small, so my moment will also be small. My m theta curve will be more or less linear, and loading and unloading will also take place along more or less same path. Then what will happen? In the negative direction, it is going slightly more. But loading and unloading both are occurring almost along the same path. And then from here, further loading will occur. It will go higher. And when I start unloading from here, it will go furthermore. Just a minute. So till now our section has not yielded. Okay, so you can see that it will increase. Okay, as I am increasing the theta, the moment is increasing. Now let us say if I go back from here, okay, suppose here the yielding occurs. Then what will happen beyond yielding? The increase in the moment will be less with theta. So you can see that the shape of the curve has changed. And if I start unloading from here, it will be almost parallel to the initial, but you can see that there will be a permanent rotation. This permanent rotation, a small permanent rotation is occurring in each side, but it will go on increasing. And then if I go in the other direction, what will happen? It will go like this. And then it is not going to increase much, the moment will not increase much, but theta will go on increasing. Okay? So, do you understand? Initially, the moment will also increase with theta. After yield, only theta will increase, moment will not increase. That's what this curve shows. This is in monotonic load, and this is under cycle.
So the increasing theta is due to increasing moment.
Increasing theta is equal to increasing moment.
Increasing theta is due to increasing moment.
Okay, and maybe vice versa also. Either you can apply a displacement, and whatever force is required for giving that displacement, that you can measure, or you can apply a force, and then whatever displacement is occurring, you can measure that. So either of the two you can apply. Either you can apply a displacement or you can apply a force. Here I am applying displacement.
Okay, then after some point.
So as I am going on increasing the displacement, initially the moment will increase in the same proportion, elastic condition.
Yes.
So you can see as displacement is increasing, moment is also increasing. Then what will happen? Moment will start, or the rate of increase of the moment will start reducing, or the slope of n theta curve will go on reducing.
Why?
Because of this curve. Suppose from here I unload it, okay, and bring it here. What it cannot go here. Can it go?
No.
Because this is the maximum capacity which we have achieved in monotonic condition. Okay. Now what do you think? The moment at any displacement here, any curvature or displacement, I told you curvature and displacement and rotation are related. So I calculate a moment here, and let us say same theta corresponding to this phi, I calculate this moment here. Will these be same? Under monotonic and cyclic load? What do you think? Why? Because of the degradation. Okay. Kavan, can you give that presentation? You have that presentation?
Both the PDFs I've copied, which you have given.
Okay. Okay, let's open that. Because that is a realistic plot, I can better explain it there. We have to. This one? No, this will not go. You cannot come this. You have to go up. Go up. Further. Further down. Further down. Yes. Hmm? Okay. Okay. So you see here, this is the behavior of a steel column. Okay. Subjected to cyclic load. पेन को ऑफ करना पड़ेगा.
नहीं सोना चाहिए सर.
और पेन कहाँ से आएगा? इससे आएगा.
क्या क्या?
पेन
हाँ फ्रंट साइड.
इससे.
हाँ और यहाँ पे पैन.
Okay, so let us take one displacement here. This. Corresponding to this displacement, if you see successive cycles, the first cycle was this, then second cycle, third cycle. So if you see at the same displacement as the successive cycles are occurring, the capacity has reduced a little bit. This is steel, okay, which is quite ductile. Here you can see that reduction is less. Let's see what happens in case of नीचे जाओ. You see here, this is RCC. So look at these curves carefully. One curve is this, and if you see here, first cycle, second cycle, third cycle, fourth cycle, fifth cycle. Let's go to masonry. Here. First cycle, second cycle, third cycle, fourth cycle. Color change हो जाता है. Okay, every time this color will change. You can see every time the strength reduces. Why? Because I told you under cyclic load there is accumulation of damage. There is accumulation of damage in steel. There is accumulation of damage in concrete. And how much accumulation of damage will occur? That depends on ductility of that particular material. In steel, at a given displacement, less damage. In concrete, more damage. In masonry, even more damage. Okay, so if you compare these curves, so if you compare this curve with this curve and with this curve, do you see any difference? What is the difference? Area is reducing and cyclic degradation, we call it cyclic degradation. Cyclic degradation here is much less. Here the cyclic degradation is more. Here the cyclic degradation is. Cyclic degradation in what? Cyclic degradation in strength. Okay, and also in stiffness. What is the stiffness in successive cycles? If you take the slope so if you see the slope here, in this cycle it is this much, in this cycle it is this much, then so you can see that the slope is also reducing. Slope of q delta or m theta or m phi, it is representing stiffness. So stiffness is also reducing in successive cycles, strength is also reducing. So this is cyclic degradation of stiffness and strength. So under cyclic load, the stiffness and strength at any given displacement reduce. Initial range, this degradation is less, but as we move ahead, larger displacement we apply, cycles of larger displacement we apply, the degradation is also more. Secondly, you see here the area has reduced. This portion of the curve is becoming narrower and narrower. Okay. This is called pinching. So the area of the hysteretic loop reduces. So under cyclic load, these three parameters come into picture. Okay, there is degradation of stiffness, there is degradation of strength, and there is pinching. Okay, the monotonic curve, which I have taught you, that cannot take these three effects into account. Okay, so it is sort of an envelope. My cyclic curve cannot go this behavior, which we call hysteresis, and this plot we call hysteretic curve. So hysteresis curve cannot go outside the monotonic curve. So that is like an envelope on that. Yeah, but it will be below that. Okay. So during earthquake, our structure will be subjected to cyclic load. So the structure will undergo degradation of stiffness, it will undergo degradation of strength, it will undergo pinching. Okay. The monotonic solution which I have given you, the method of calculation of moment curvature, it does not take this into account. Okay. That is based on monotonic behavior if I am going on pushing my structure in one direction. So it will give you an envelope, but not the real behavior. Okay. How we can get real behavior? So far, the only reliable way of getting real behavior is experiment. People are trying a lot of numerical techniques. You will see different types of formulations are there. They have fiber element. Okay. In fiber element, they consider the section consisting of number of fibers. Each fiber is made of some material, either concrete or steel, and the cyclic behavior of that material is specified. And using that, they are trying to predict the behavior of the whole member numerically. Closed form solution is not possible. Okay. So far, we have used closed form solution. That is applicable only in the simple case where we are assuming plane sections to remain plane, we are assuming strain compatibility, we are assuming that stress strain curve is known. Okay, that is there only in case of monotonic. Okay, so obtaining this cyclic behavior analytically is not possible. Numerically, we can do it, but still very reliable model for this. After quite complex calculations. You will see some of you will do literature review on that. So you will see that quite complex calculations people have performed, but still they have not been successful. So what is the possible way? Experiment. So people have conducted a lot of tests. You see in our lab also we are conducting tests. So they have conducted a number of tests, and based on those tests they have obtained what we call generalized model. Okay. So generalized model in terms of what we call backbone curve. And what is backbone curve? If we plot the envelope of this curve, this envelope, if we plot, this is called backbone curve. So this backbone curve is able to consider cyclic degradation of strength. Can it consider cyclic degradation of stiffness? No. Can it consider pinching? No. This backbone curve can consider only the one effect of cyclic loading, that is cyclic degradation. But that's also quite significant. Okay. And how do we do it? So the actual behavior we get from experiment, and then we plot envelope. You can understand this envelope will be below the monotonic moment curvature curve or monotonic load displacement curve. Monotonic load displacement curve, if I show along with this, how would have that gone? Initially both will be same, but after that the difference will occur. Monotonic curve will be higher and it will go larger displacement. Under cyclic load, failure will occur earlier, strength will be lower. Initially both curves will be same. So this is monotonic, this is cyclic, and this is backbone. Backbone curve is envelope. So you can see up to yield here, both curves are same. Even slightly beyond yield also, both curves not much difference is there. But at larger displacement, the curves are very different, and the ultimate rotation is very different. Under cyclic load, it can resist less ultimate rotation. Under monotonic load, it can go for large rotation. Okay, so whatever calculations I have shown you, that has limitation. Okay, if I am interested, and in case of earthquake I am interested in cyclic behavior, so that can be obtained from experiment. How will you conduct experiment? If you have to design a building, will you go and conduct experiment first? No. So ASC 41, this is started from FEMA 273. I do not remember the exact year, but this was something close to 1990 when this started. So 90 FEMA 273. That document came. Then FEMA 356 came. Then AC 41 came, and now AC 41 also several revisions have come. The latest is AC 41 70. 2023, the next revision is expected. Okay, so this is the latest one. There, what they have done, based on whatever database of experiments have been conducted world over, they have collected that, and using that database, they have developed the backbone curve parameters, okay, for different detailing, okay, and different types of columns, RCC columns as well as steel columns. So in ASC 41, you will find chapters corresponding to steel and concrete, okay, and there this backbone curve is given in terms of what we call generalized backbone curve. What is generalized backbone curve? That the shape of the backbone curve is represented by this idealized shape. So this is an idealized backbone. Okay. So the hysteresis here, just to visualize how the hysteresis is happening. And then it is reducing like this. So this point is important, B point. What it is representing? It is representing yield, not first yield, yield point. Okay, that's why you can see it is not exactly on my curve. Then this point C, this is important. Okay, what is this representing? No, it is not 5. It is representing when the concrete gets crushed. Okay, steel has not yet ruptured. Concrete gets crushed. And what will happen when the concrete gets crushed? I have a cantilever. It was subjected to the cyclic load, and the reinforcement, if it is to be subjected to cyclic load, reinforcement has to be. So the concrete here has got crushed. Will it fall down? What will happen when the concrete has got crushed?
Steel will come into picture.
So concrete is not there. Can steel alone resist movement?
Yes. Bottom steel and bottom.
Suppose I have a column in which only steel is there. This is steel. No concrete, only steel. Can it take load? Bangalore में गिरा ना वो कॉलम का केज, one person, one lady and the kid died. That was only steel. So can this cage alone can take load? No. So how it is resisting? Think of another case where this is the concrete and here is the steel. The steel is still intact. Will it be able to resist the load? Moment. It will. How? First it will rotate and then the concrete will come in contact here. Steel it can take some moment. This is called catenary action. What is catenary? You have heard this word earlier also. What is a catenary? Catenary is a specific curve in geometry. What is that curve? Which curve is a catenary? So deformed shape of electric cables on pole. Okay. So when this does not have any bending capacity. Okay. The cable. What is a cable? Which can take only tension, which cannot take bending. So when it is hung at the two ends, that is catenary. How it is coming in the beam? It is coming from simply supported beams. Suppose this simply supported beam, it is subjected to increasing load. Where will the hinge form? At the support?
No.
If it is simply supported, then it will form at the center. And the concrete at the center will get crushed. When the concrete at the center will get crushed, still it is not going to fall down because this is steel at the bottom. This will keep it hanging. Capacity will reduce drastically, but it will not fall down. Okay, this is called catenary action. Something similar will occur at the fixed end also in case of the catenary. So even though this concrete here has got crushed, this steel can still have some residual capacity, and that residual capacity is given by this steel. And this is where the failure occurs. So up to B, let me remove all this. Up to B, it is elastic. How can you get this delta here, delta or delta? From the moment of inertia, effective moment of inertia of the member. Okay, so EI effective, which is 0.3 times or 0.35 times BD cube by 12. Using that, you can calculate this delta Y. Beyond that, it is plastic deformation. So this is plastic deformation, and beyond this, it is elastic deformation. So this is elastic, this is plastic. And here, the failure level. And here C, here crushing of concrete. पूरा चला जाएगा ना? Here crushing of concrete. Yeah. And these two values, A and B, these are important. What are these? These are representing theta P or delta P. Okay, corresponding to concrete crushing and corresponding to failure, corresponding to rupture. What about
D?
D? This one. This is almost vertical. Means whatever is that displacement at concrete crushing, almost same is here. There is very little difference in the two. So when the concrete character, suddenly the strength reduces. So there is sudden reduction in the strength. Okay. So you can see in very little displacement, just 1 or 2 cycles there, and the strength reduces when the concrete gets crushed. And then we have this residual capacity C. So these 3 parameters A, B and C. If I give you these, you can generate the generalized backbone curve. And what is the difference between a backbone curve and moment curvature curve? Backbone curve is for cycle. Okay. So you need these values of A, B and C. From where you will get these values? AC 40. How? I will just show you. Sorry. So first of all, here the effective stiffness is given. There is a table. You can see this table. Effective stiffness is here. For beams not pre-stressed, it is 0.3 ECEIG. What is ECEIG representing? Effective modulus of rupture. Sorry, modulus of elasticity of concrete. Okay, expected. Sorry, this capital E is corresponding to expected. So it is expected and 30% of that. Okay, this is shear rigidity. How much is the shear rigidity for a steel beam? Where no cracking. Suppose we are not considering any cracking, then how much will the shear rigidity? Similar to fractional rigidity, which is EI, shearing rigidity is G into AR. Okay. And what is the relationship between G and E? G is equal to E.
G equal to
Suppose we take mu is equal to 0.15. How much is G? Can you calculate in terms of E? Concrete Poisson's ratio we consider equal to 0.15. Or let us take 0.25 or to simplify our calculation. Mu we take 0.25. 0.4. So it is that. I don't see anything. How to go back? I want to go back. For the pan right. So you can see that this is 0.4E. So sometimes people get confused that we are reducing this to 0.4. We are not making any reduction actually. What is AW? The shear area or the wave area. Okay, because shear resistance comes from wave alone. Flanges do not contribute. So it is 0.4 E, which is actually equal to G. So G into A. So shear stiffness and flexural stiffness. You look at column. In case of column, when pre-stress beams are used, this is E into IG. Why?
In this case, compressive force will be additional there.
So,
which will confine more the concrete again.
Confine means
Due to
in pre-stress beams, how do we design? We design pre-stress beam not to crack. Okay, or even if those are cracking, the cracking is very minimum. Okay, there are different grades of design, classes of design. So we design pre-stress beams not to crack. And if the beams are not cracking, then gross area will be the effective area. Okay, and pre-stress beam reinforcement is nominal, so no reinforcement, so it is not cracking. So neither we need to multiply that by m because there is no steel. Okay, and cracking is not occurring, so it is as good as gross section being effective. Okay, in case of columns, if axial force is more than 0.5 AGFCE, then it is 0.7. And if it is less, then it is 0.3. Why it is more? When axial force is large, I just told you, when axial force is more, cracking will be less. Depth of the neutral axis will be more. C minus T equal to P. So if P is large, C will be large. For C being large, the neutral axis will be big. Okay, so cracked area will be less. So effective moment of inertia will be more. When it is less than 0.1 AGFCE, then it is as good as a beam. What is the difference between beam and column? Axial force is 0 in beam. So when the axial force is very small, it will be same as that of the beam. So this is the effective stiffness, and then it also provides the table this is for steel, I will come to this later, for RCC. So what you see here, A, B, C, okay, and on what it is depending? I told you to develop the generalized backbone curve, what you need? Values of A, B and C. So values of A, B and C are given here. And what are these A, B, C? These are theta, rotation. Which rotation? Chord rotation. And what is the unit of rotation? Radian. So these are in radian. Okay. And this theta is also delta by L. So A, B and C is the residual strength. Okay. So these A, B, C are given for different conditions. What are the different conditions? One condition is rho minus rho dash over rho balance. Rho minus rho dash over rho balance. Rho is tension reinforcement ratio. Rho dash is compression reinforcement ratio. Okay. And rho balance is the balance ratio. Balance reinforcement ratio. So If tension reinforcement is more, rho minus rho dash by rho balance will be positive, greater than 0. If compression reinforcement is more, then this will be negative. Can compression reinforcement be more than tension reinforcement? Yes or no?
Yes.
How? Where? Why? At the joint in the beam, when it is subjected to sagging. Okay. You can ask why the beam will be subjected to sagging at the joint. Because earthquake is reversible. So for one direction of the earthquake, this joint will be subjected to hogging, this joint will be subjected to sagging. When earthquake reverses this direction, this will be subjected to hogging, this will be subjected to sagging. The requirement of the reinforcement in hogging is more. Why? Because the gravity and earthquake moments in hogging gets added up. Gravity is always causing hogging moment at the joint. Tension is at the top face in gravity. Earthquake is reversible. For one direction, it will cause tension at the top. For other direction, it will cause tension at the bottom. So when you are designing for the extreme case at the top, where gravity and earthquake both are additive. So the top reinforcement is invariably much more than the bottom reinforcement. But this section will be subjected to sagging also due to reversal of earthquake. In that case, the reinforcement in compression will be more, in tension it will be less. So that situation is also possible. So the behavior at the joint will not be symmetric. In hogging it is going to be different, in sagging it is going to be different. Okay, and that's why this value of A, B, C will also change. So one is this reinforcement ratio in compression, tension. Okay, another one is the C and NC. What does that mean? Conforming and non-conforming, or compliant or non-compliant transverse reinforcement. This is corresponding to transverse reinforcement. What is compliant? When you have followed IS 13920, ductile detailing has been followed. Okay, actually they are referring to ACI 318, but the provisions of ACI 318 and IS 13920 are same. So if you have followed IS 13920, then it is C. If you have not followed IS 13920, then it is NC. And then it also depends on the shear stress at the joint. Suppose the shear stress is more, then what will happen? The point at which concrete will get crushed, the displacement at which concrete will get crushed will reduce. It may also happen that initially the failure occurs in fracture, the cracking occurs, not failure, but the cracking occurs in fracture, and when the concrete gets cracked in fracture, then the intact area reduces and then it may fail in shear. Okay, so shear stress present at the location of yielding, that is also important. So this is given in terms of B over BWD FC dash, square root FC dash. Square root FC dash is proportional to the shear capacity or shear strength of concrete. Okay, and B into D, or rather BW into D, that is the shear area. Okay, so this is giving the shear capacity, this is the shear demand which we are having. So shear demand to shear capacity ratio. If it is less, then value of ABC will be more. If it is more, then value of AB will be less. Okay, so which case you think you will be most ductile? When rho minus rho dash by rho balance is less than or equal to 0, isn't it? The compressive reinforcement should be either more than the tensile reinforcement, that means it is under reinforced. So when rho minus rho dash by rho balance is less than or equal to 0, okay, and when V by BW D FC dash is minimum, that is 3, okay, and it is compliant. So first case you will see, you will get the maximum value of B 0.05 radius. Can you calculate B for monotonic loading in your case? Can you calculate B? How you will calculate B? What is B actually giving us? In our monotonic case, what was B? Yes? 5P. Not 5P, it is rotation. Theta. So theta P there. How we have calculated theta P? Theta U minus theta Y. What was the condition at theta U? The concrete has got cast. Okay? So theta P is actually B. So this B is theta P under cyclic condition, which we have obtained in our case. Okay? So you can compare it with that, what you have obtained. And point 2 is the residual strength. Actually, this is very uncertain. So you can see in all the cases they have given point 2. Okay? Because in many test cases, in many experiments, this value has not been obtained. They have not tested up to that level, or this has not been obtained. So just they have given an average value of C, and it does not have much significance also. So this is very important for us, this P. Okay? So can you plot now the moment rotation or load displacement curve under cyclic condition using AC function?
So, to
Yes.
degree of tensor reinforcement, there is tension with respect to the total reinforcement.
Sorry, I couldn't attention. Ratio is ratio of steel divided by ratio of concrete. Area of steel divided by area of concrete. So this is AST by BD.
When balance means row balance and
Row balance means that whatever is required for balance failure. So IS 456 gives us for balance failure the reinforcement ratio corresponding to balance failure. That is row balance. Okay. Look at the assignments. Is anything remaining? Or we have done everything? Only to a concrete because cover has already covered now. Okay, so we have covered all the topics related to tutorial. Now you tell me when you are submitting. You have to decide the date as in the last semester, and then you have to honor. And I told you I will not mind even if you decide next semester. But you decide. Then you.
This surface is showing as L5.
No. Yield surface is not alpha. Yield surface is PM interaction. Why we are calling it surface? Because this is P and MX, M1. So actually it is surface. What is given in IS 456 or SP16. So yes, when do you want to submit? Submission date you can decide, but it will be there in midterm exam. Whether you submit or you do not submit.